In this video, I'm going to present my results of my experiment about constant velocity and Newton's second law. For the experiment, I used a gymnastic ball with a mass of 3 kg. I put the origin of the coordinate system in the center of the ball, which is rolling from right to left. As a measuring stick, I used a measuring band with a length of 20 centimeters, you can see over there. For the analysis, I observed the frames 110 to 126 while having a frame rate of 29 frames per second. For the computer model based on Newton's second law, I used the data from the experiment I've shown to you. The initial position was at 0.003 meters. To calculate the initial velocity, I used the first two lines of data in order to calculate the average velocity and take it as the initial velocity, which shows to be about minus 1.706 meters per second. In the code, I set the mass of the ball to 3 kg, but it becomes apparent that the mass of the system is irrelevant when observing a constant velocity. Furthermore, I set the initial conditions, which I mentioned a moment ago, so the initial position of the ball at 0.003 meters and the initial velocity of the ball at minus 1.706 meters per second. I also set the time step delta t to 0.034 seconds, which is the time between two frames. I calculated that through the frame rate of 29 frames per second. I used this time step to have the same amount of data to compare. Next, I set the network force to 0, which is the main assumption when working with constant velocities. As you can see, the term Fnet over the mass of the ball m times delta t gets 0 because Fnet is 0, so our velocity ball val is constant and the graph, which is produced through the data, will be a straight line. Now I will show you my computer model. Here you can see the results of my experiment in the graphs. The horizontal line is the time in seconds, and the vertical line is the displacement in meters. We can see that both graphs are straight lines, so both of them have a constant velocity. The reason why these two graphs look like a straight line is Newton's second law. This law states that Fnet over m is equal to delta v over delta t. This is the same as Fnet over m is equal to Vf minus Vi divided by delta t. Multiplying delta t and adding Vi leads to the equation Vf is equal to Fnet over m times delta t plus Vi. If we set Fnet to 0, what we are doing when we are looking at constant velocities, Vf is equal to Vi, so V is constant. But we want to know why the graph of the displacement time diagram is a straight line. We have the formula Vf is equal to delta r over delta t. When we multiply delta t, we'll get delta r is equal to Vf times delta t. We can write that as Rf minus Ri is equal to Vf times delta t. When we are now adding Ri, we'll get Rf is equal to Vf times delta t plus Ri. This looks similar to the slope-intercept form of a straight line, y is equal to mx plus b. So our displacement time graph is a straight line with Vf as the slope. So both of the graphs describe a motion with constant velocity. But when we are comparing the graphs of the data of the experiment, which is the blue line, and the data of the computer model, which is the red line, we can see that between the begin and somewhere between 0.6 and 0.7 seconds, there is a congruence of the graphs. But later the discrepancy gets bigger and bigger, which shows me that there is a failure in my computer model, which I haven't found yet. Later I found out that the failure in my model was the initial velocity, which used to be minus 1.706 meters per second, when using the average velocity of the first two lines of data from the experiment you can see over here. But when you're using the average velocity between the second and the third line, you'll get an average velocity of minus 1.4 meters per second. When using this as the initial velocity, the graphs fit much better than with minus 1.706 meters per second as the initial velocity. Now I'll show you the graphs with the initial velocity of minus 1.4 meters per second. As you can see, the graphs fit much better and the discrepancy is lower.